we are moving. Right now, you and I are hurtling through space at incredible speed. The Earth is spinning. It's also orbiting the sun. That's a fast trip. The sun itself isn't sitting still. Now, it's moving too, dragging our entire solar system along with it. It orbits the center of our galaxy, the Milky Way. This is a huge, slow journey that takes over 200 million years to complete. But that's not the end of it. The whole Milky Way galaxy is also on the move, and it's moving fast. Very fast. About 600 kilometers per second, that's over 1,000,000 miles per hour. So the next question is pretty simple. Where are we going? For a long time, we didn't have a good answer. We just knew the universe was expanding. Everything was moving away from everything else, like dots on an inflating balloon. So we should be moving away from other galaxies, but our motion is a little different. It's not just random, it's not just part of the general expansion. Our galaxy and all the galaxies near us seem to be heading in a specific direction. There's a current, a cosmic river, and we're caught in it. Something is pulling us. Astronomers gave this something a name. They called it the Great Attractor. It's a great name for a great mystery. It sounds like something from a science fiction story. A giant, unseen object in the depths of space, reeling in galaxies like fish on a line. The truth is a little more complicated and a lot more interesting. It's a story about seeing the invisible and mapping the universe on the grandest scale possible. And it all starts with the faint echo of the Big Bang. After the Big Bang, the universe was a hot, dense soup of energy and particles. As it expanded and cooled, this energy was released as light. This light is still traveling through the cosmos today. It has stretched out over billions of years, becoming very long, cool microwaves. We call it the cosmic microwave background, or CMB. It's everywhere. No matter where you point a radio telescope, you will find this faint, ancient glow. It's the oldest picture of the universe we will ever have. In the 1970s, scientists made very precise maps of the CMB. They expected it to be almost perfectly uniform in all directions, and it was, mostly. But there was one strange anomaly. The CMB was not quite the same temperature everywhere. On one side of the sky, the microwave light was slightly warmer, meaning its wavelengths were a tiny bit shorter. On the opposite side of Thesky, it was slightly cooler, meaning its wavelengths were a tiny bit longer. This pattern is a dead giveaway to astronomers. It's the Doppler effect. You know the Doppler effect from everyday life. It's the sound a siren makes. When an ambulance is coming towards you, the sound waves get compressed. The pitch sounds higher. As it moves away, the sound waves get stretched out. The pitch sounds lower. The same thing happens with light. If something is moving towards you very fast, the light waves it emits get compressed. They shift towards the blue end of the spectrum. We call this a blue shift. If it's moving away, the light waves get stretched. They shift towards the red end of the spectrum. This is redshift. The cosmic microwave background is the ultimate reference point. It's the backdrop of the entire universe, and it was telling us that we were moving relative to it. The hot side of the sky was the direction we were headed. The cold side was the direction we were coming from. The data was clear. Our solar system, our galaxy, our entire local cluster of galaxies were all moving together at this tremendous speed towards a particular point in the sky. This was a huge discovery. It confirmed we were part of a large-scale flow, but it raised a much bigger question. Why? What could possibly have enough gravity to pull an entire galaxy and all its neighbors through space? The general expansion of the universe couldn't explain this directed motion. This was something else. This was a local, powerful pull. To find the source of this pull, we needed a map. Not a map of stars, but a map of galaxies. We needed to know where the big concentrations of mass were. In the universe, mass means gravity, and gravity is what moves things. The problem is, mapping the universe is hard. Like space is big and it's mostly empty, galaxies are the landmarks. To map the galaxies, we use redshift. Just like the CMB, the light from distant galaxies is also stretched by their motion. In the 1920s, Edwin Hubble discovered that almost every galaxy he looked at was redshifted. And the farther away a galaxy was, the more redshifted it was. This was the first evidence that the universe is expanding. Everything is moving away from everything else. So, to find the Great Attractor, astronomers had to look for something extra. They had to measure the expansion speed of thousands of galaxies. Then they had to see if there were any deviations from that smooth expansion. Imagine a river flowing steadily towards the sea. That's the expansion of the universe. Now imagine a small whirlpool or a strong current in one part of that river. That's a gravitational attractor. It's a local deviation in the overall flow. Finding it meant painstakingly measuring the speed and direction of countless galaxies to see which way the cosmic river was really flowing in our neighborhood. In the 1980s, a team of astronomers who became known as the Seven Samurai took on this challenge. They spent years at different observatories measuring the motions of about 400 galaxies in our cosmic vicinity. When they put all their data together, they saw the pattern. The galaxies weren't just moving away from us as part of the Hubble expansion. There was a coherent, large-scale motion. Galaxies for hundreds of millions of light years in every direction were all streaming towards the same point in space. They had found the source. They calculated that this massive concentration of matter had to be located about 150 to 250 million light years away from us, in the direction of the constellations Centaurus and Hydra. They estimated its mass had to be enormous, something like tens of thousands of times the mass of our own Milky Way galaxy. This was the gravitational anomaly they were looking for. They gave it the name the Great Attractor. But there was a huge problem. When they looked in that direction with optical telescopes, they couldn't see anything big enough to explain the pull. There were galaxies there, sure, but not enough. Not nearly enough to have the gravitational muscle to pull in our entire local group of galaxies. Where was all the missing mass? The answer was hiding in plain sight. Or rather, it was hiding behind our own galaxy. The center of the Great Attractor lies directly behind the plane of the Milky Way. This region of the sky is called the zone of avoidance. It's not called that for any mysterious reason. It's called that because it's incredibly difficult to see through. Our galaxy is a flat disk, like a frisbee. We live out in one of the spiral arms. When we look towards the center of the galaxy, or through the disk, our view is blocked by a thick screen of stars, gas, and cosmic dust. This dust is like a thick fog. It absorbs and scatters visible light, making it almost impossible to see the distant galaxies that lie beyond it. So, the Great Attractor, this massive thing that was shaping the fate of our part of the universe, was located in the one place in the sky that was hardest for us to observe. It was a cosmic coincidence of the worst kind. For years, the Great Attractor remained a mystery. We could feel its pull. We could calculate its location. But we couldn't see it. Science, however, has more than one way to see. Visible light is just one small part of the electromagnetic spectrum. Other types of light, like radio waves, infrared, and X-rays, have longer wavelengths. These longer wavelengths can pass through the dust and gas of the Milky Way more easily. It's like how you can hear the bass from a car stereo from far away, even when you can't hear the higher-pitched treble. The long sound waves travel better. The same is true for light. So astronomers started pointing different kinds of telescopes at the zone of avoidance. Your radio telescopes could detect the cold hydrogen gas in distant galaxies. Infrared telescopes could see the heat from stars that was otherwise blocked by dust. X-ray telescopes could spot the superheated gas that collects in the middle of massive galaxy clusters. Slowly, a picture began to emerge. Peeking through the cosmic fog, astronomers found what they were looking for. Right in the heart of the Great Attractor region, they discovered a huge, previously unknown supercluster of galaxies. They named it the Norma Cluster. It's a sprawling collection of hundreds of galaxies all bound together by gravity, and it's very massive. Later surveys found other clusters nearby, all part of a larger structure. So, mystery solved. The Norma Cluster and its neighbors were the Great Attractor. Well, yes and no. The mass of the Norma Cluster and the other visible galaxies was significant. It was a big piece of the puzzle, but when astronomers did the math, it still wasn't enough. The mass they could see even with their new instruments only accounted for a fraction of the gravitational pull they were measuring. The motion of our galaxy was still too fast. There was still something missing. This is where the story takes a turn. The idea of the Great Attractor as a single, massive thing started to change. What if it wasn't an object, but a location? What if it wasn't a cosmic monster pulling us in, but more like the bottom of a giant valley in the fabric of space-time? This led to a new way of mapping the universe. Instead of just looking at where galaxies are, scientists started focusing on how they are moving. By analyzing the peculiar motions of thousands of galaxies, their motions on top of the general cosmic expansion, they could build a map, not just of matter, but of gravity itself. They could map the cosmic flows. In 2014, a team led by astronomer Brent Tully published a new map of our local universe. They redefined our place in the cosmos. They showed that our Milky Way galaxy is part of a vast supercluster far larger than anyone had realized. They named this supercluster Laniakea. In Hawaiian, it means immeasurable heaven. Laniakea is immense. It's over 500 million light years across and contains about 100,000 galaxies, including our own. The best way to think about Laniakea is not as a collection of galaxies, but as a gravitational basin. Imagine a watershed on Earth. All the rain that falls within a certain area flows downhill in streams and rivers towards a single low point. Laniakea is a cosmic watershed. Every galaxy within it is flowing downhill along the contours of gravity. And the Great Attractor, it's simply the central valley, the lowest point in our part of this enormous structure. So, the Great Attractor isn't a single object pulling us in. It is the gravitational focal point of our home supercluster. We are moving towards it because it's the bottom of the gravitational hill we live on. All the mass of the 100,000 galaxies in Laniakea, including the Norma Cluster, combines to create this large-scale structure. Our motion is just a natural consequence of living within it. It's gravity doing what gravity does, on a scale that is difficult to comprehend. This new perspective solved a big part of the mystery. The missing mass wasn't missing at all. It was just spread out over a much larger area than originally thought. The Great Attractor isn't one thing over there. It's the combined pull of everything around us, defining the very landscape of our cosmic neighborhood. But the story doesn't end there, because even cosmic superclusters are not isolated. When you zoom out even further, you see that Laniakea itself is moving. Our entire supercluster, all 100,000 galaxies, is being pulled towards something even bigger. Further out, in the same general direction as the Great Attractor, lies an even more massive concentration of galaxies. It's called the Shapley Supercluster. It was discovered by Harlow Shapley in the 1930s. It is the largest and densest concentration of galaxies in our corner of the universe. It's a true cosmic behemoth about 650 million light-years away. Compared to the Shapley Supercluster, our Laniakea is just an average suburb. The gravity of the Shapley Supercluster is so immense that it's pulling on everything for hundreds of millions of light-years around it, including our own Laniakea. So the cosmic flow is more complex than we first thought. We are flowing downhill towards the Great Attractor region within Laniakea. But the entire Laniakea basin is itself tilted and flowing downhill towards the even deeper gravitational well of the Shapley Supercluster. It's like a small stream flowing into a river, and that river is flowing into a giant ocean. Our motion is a combination of these nested gravitational pulls. The Great Attractor is our local destination. The Shapley is the regional one. And just to make things even more interesting, scientists have recently discovered that it's not just about what's pulling us. It's also about what's pushing us. Gravity is a force of attraction. Mass pulls other mass towards it. But what about a lack of mass? A huge, empty space with very few galaxies would have a much weaker gravitational pull than the areas around it. Relative to the dense regions, this void would act like a repeller. It's not a real pushing force. It's more like a gravitational desert. The pull from all other directions is stronger, so you get pushed away from the empty spot. By mapping the motions of galaxies, astronomers have identified a huge void located behind our Milky Way galaxy. It's been named the Dipole Repeller. It's a vast, underdense region of space, and it seems to be pushing our local group of galaxies away from it, contributing to our overall motion. So our journey through space is a cosmic dance. We are being pulled from the front by the Great Attractor region and the more distant Shapley Supercluster. And we are being pushed from behind by the Dipole Repeller. Our velocity of 600 kilometers per second is the result of all these gravitational tugs and shoves playing out over unimaginable distances. So what does this all mean for us? Are we on a collision course with the Great Attractor? Will our galaxy smash into the Norma Cluster one day? The answer is almost certainly no. And the reason is dark energy. The universe is not just expanding, the expansion is accelerating. There is a mysterious force, which scientists call dark energy, that is pushing everything apart. This force is a property of space itself, and over very large distances, its effect is stronger than gravity. So, while we are moving towards the Great Attractor region, the space between us and it is also expanding. It's like trying to run up a downward moving escalator. We are making progress relative to the escalator steps, but the escalator itself is moving against us. At the moment, our local gravitational pull is winning, and we are getting closer. But as the universe continues to expand at an accelerating rate, the space between us and the Great Attractor will stretch faster and faster. Eventually, the expansion will be so fast that it will overwhelm the pull of gravity. The Great Attractor will be carried away from us faster than we can travel towards it. We will get closer for a few billion years, but we will likely never reach it. The story of the Great Attractor is really the story of us figuring out our address in the universe. We started on a planet, then realized we were in a solar system. Then we found our place in a galaxy. Then we discovered we were part of a local group of galaxies. The Great Attractor forced us to look bigger. It led us to discover our home in the Laniakea supercluster, a structure so vast it redefines what local even means. It showed us that the universe isn't a random spray of galaxies, but an intricate connected web of structures, a cosmic web of clusters, filaments, and voids. The Great Attractor isn't a monster or a single destination. It is the shape of home. It's the gentle, persistent, and inescapable pull of all the matter that we share this corner of the cosmos with. It's the sum of everything around us. It is the direction that gravity has chosen for us, a silent current carrying us through the immeasurable heavens. And the search for it has taught us more about the grand scale of the universe and our place within it than we ever thought possible. We are still moving, and we are still learning where we are going.